Welcome to the video lesson on linear optimization part 2, also known as the tricks of the trade. I'll take you through two different trick things that come up frequently in this topic. And the first one is that it could happen that within your polygon of constraints, one or more of the constraints are not included, does not have the line underneath. And if that is the case, then even though typically the rule is that the maximum or the minimum has to occur on the outside, on the border at one of the vertices, that is not true here, because anything on a broken line does not count. It's not included. So even though you will still have to do the work to find the coordinates of a polygon of constraint vertex, that might not be the best point. You might have to look inside. So here's an example. Suppose that in this case, which is an example which is in the other video, what if we made this change here? Imagine if this here on the line y is less than or equal to 300, if we change it to y is strictly less than 300, because originally our maximum in this situation had happened at point C, which is both on this line and on this line. If we made this line not included, if we change that to be a strictly less than, then this would have changed to be a broken line. And then anything on that line is excluded. So that point would no longer have been included. What would we do in that case? Well, points C and D, these two are both excluded from the mix. So does that mean that our new maximum happens at point B and that is $50? Great question, but the answer is no. So those points there are excluded. So we have a couple of options. Looking at point B is one of them. If point B was a very close second place, that might have replaced this one as the maximum. And sometimes, and in some cases, that could be what happens. But it also could happen that in this case, because this difference is significant compared to what the profits were, we might look inside the shape, somewhere inside this gray shaded area that's very close to, but not exactly at point C. So this was a situation where we were looking at the number of pencils and calculators originally, and the number of pencils and calculators have to be whole numbers. So some points that are close to 10, 300 could be, let's say, 10 and 299, because we know that we have to have a y value that is strictly less than 300. So we could pick something just a little bit below that point. So still have 10, but have 299 pencils instead of 300. It satisfies that constraint. It still satisfies the other constraints. So the question would be, what would the profit be at that new point if we tried that point at 10, 299? And in this original example, the profit had been $2 for each calculator and 15 cents for each pencil. If we plugged in these values, then rather than $65, we would have gotten a profit of 64 and 85 cents, which still beats B, and it's very close to what the previous max was. You might try something like, it's possible that if you went up to 11, there could be a point over here that might best that profit. And so you might have to check that. You might have to find a point that's there that still satisfies all the constraints. But that's what that trick entails, and it's not an easy thing to do. So that's trick number one. The second type of tricky question that could come up is that you will be asked to find the number of solutions, how many solutions or how many points optimize a situation. And the trick is that if there is more than one point that has the same max or the same min value, not only are there two, but actually all the points in between have the same value too. I'll show you what I mean by that. That says veil, but it should be value. So for example, there's a dry cleaning service. They dry clean dresses and suits. The profit is $4 per dress and $8 per suit. So this is one where you're already given the polygon of constraints. And there are going to be three different questions that I'll take you through. The first one, question A, is how many solutions maximize the owner's profit? That's a common question. So what do you do? Well, first you'll set up a table to count out the coordinates of each vertex. If you want to do that on your own, you can pause and try it. I'll just show you what the answers are. The vertices A, B, C, and D have these coordinates. So that's the first step. The second thing you would do is to calculate the value, which in this case is the profit, at each vertex. So our profit is $4 times the number of dresses, 4x, plus $8 for each suit. And if I plug that in, I will get the profit for each one. And if you want to, again, pause and try it, see if you get the right thing. These are the profits that I got. So pause now if you want to try it. That's the profit at each point. So you might be tempted to say, oh, okay, well, there's two different points that have the same max. There are two different solutions that maximize the profit. But in fact, the third thing is to find how many points there are in between those two. If it says that we're dealing with integer numbers. Like here, we're looking for a number of dresses and a number of suits. You can't dry clean half of a suit. If your suit is half dirty, you still have to pay the full amount to get it clean. So these 2 points are here. The points in between, I'm going to zoom in a little bit. The points in between those two that are whole numbers are here. I can't go here because this one has a half number of y, which is suits. This one works. That's on an even number, a full integer number of x's and y's, and so is that. And there are no others in between a and b. I'm only looking on the line between a and b because a and b were the 2 points that had the highest value. They had the maximum profit. So there are 3 additional points in between, and what that means is that the answer is that there are 5 solutions that maximize profit. 1, 2, 3, 4, 5. You could also be asked, what are the solutions? And a question like that is looking specifically for the points, the coordinates that maximize. So 5, 13, and 13, 9, that means 5 dresses and 13 suits, or 13 dresses and 9 suits. Those are 2 of the solutions. But there are others, those points that we just circled. If you counted out their coordinates, and if you want to pause and try it, you can. Those other ones have these coordinates, and those are all of the answers. What are the solutions? You can write them as points, or you could write 5 dresses and 13 suits, comma, 7 dresses and 12 suits, comma. So probably more compact to do it this way. And finally, you could also be asked, what is the maximum profit? And for that one, it doesn't matter that there are 2 points with the same, or actually, in fact, 5 points with the same profit. The max profit is just the max profit, 124. And that covers linear inequalities difficulty level 2. Thanks for watching.